Did we just change the past? I mean, seriously, what if a decision you make right this exact second could literally reach back in time and rewrite a reality that has already happened? Welcome to This Explainer. Today, we're diving into one of the absolute most mind-bending mysteries in modern physics, the infamous delayed choice quantum Weiser. It's an experiment that on the surface seems to suggest our observations in the present can literally rewrite history. But is that actually what's happening? Well, let's find out.
Okay, let's zoom way out and start with a thought experiment of literally interstellar proportions, originally proposed by the legendary physicist John Archibald Wheeler. Imagine a single photon emitted by a distant quasar billions of years ago. On its long journey to Earth, it passes a massive galaxy that acts like a giant cosmic lens, forcing our little photon to take one of two paths around it. Wheeler pointed out something completely wild. If we wait until the very last second, right before that photon reaches our telescopes, to decide how we're going to measure it, our last-minute choice seems to force the photon to retroactively alter its physical configuration, a commitment it supposedly made billions of years ago. I mean, it sounds like pure magic, right?
To actually wrap our heads around this paradox, we have to quickly ground ourselves in the classic double-slit experiment and Niels Bohr's principle of complementarity. Back in 1927, Bohr established that quantum objects, like photons, have both wave-like and particle-like attributes. The catch? You can never measure both perfectly at the same time. If you don't track a photon's exact path, it acts like a wave, passing through both slits at once and creating this beautiful striped interference pattern. But the moment you install a detector to see exactly which slit it goes through, bam! It acts like a tiny bullet, a particle, and it leaves absolutely no interference pattern at all.
The great Richard Feynman summed this up perfectly when he noted that this wave-particle dual behavior contains the basic mystery of quantum mechanics. Our measurement actually enforces a strict boundary on reality itself. By merely extracting the which path information, we destroy the wave behavior. But what happens if we get a little sneaky? What if we extract that information, but then find a way to destroy it before we even look at it?
To pull off that exact trick, physicists brought in the ultimate quantum cheat code: quantum entanglement. Entanglement happens when two particles become so intricately linked that a measurement on one immediately and predictably determines the state of the other, no matter how far apart they are in the universe. This right here is the absolutely crucial mechanism we need to perform our delayed choice erasure. Think of entangled particles kind of like a pair of telepathic coins. If you look at either coin completely on its own, it appears totally normal. It flips heads or tails, seemingly at random. But their quantum strangeness really emerges when you step back and discover that every single time coin 1 lands on heads, coin 2 inevitably, without fail, lands on heads too. So we're going to use one of these telepathic coins to hit a screen, and the other to secretly record the which path information.
So, how do we actually build this in a virtual lab? Well, we fire an ultraviolet laser into a very special crystal, usually called a BBO crystal. This crystal takes one high-energy photon and essentially splits it into two lower-energy, perfectly entangled twins. We carefully maneuver photon A toward our traditional double-slit screen, while photon B gets sent zooming off to a completely separate polarization detector.
In a famous real-world iteration of this experiment, physicists place these little things called quarter-wave plates right behind the slits. These plates do something highly specific. They perform a conditional logic operation. So if photon A passes through slit 1, it gets a right circular polarization. If it goes through slit 2, it gets a left circular polarization. Because photon A and photon B are entangled, manipulating photon A instantly entangles the polarization of photon B with that precious which path information. Alright, so the crucial point is here. We now have a physical mechanism to know exactly which slit photon A went through, just by checking its twin, photon B. But here comes the true cliffhanger of the entire delayed choice setup. What happens if we let photon A hit its detector screen first, permanently recording its landing spot, long before we even decide whether or not to measure photon B's which path information? Can our later decision actually change the pattern photon A already made in the past? Incredibly, if we use a polarizer to scramble or erase the polarization information from photon B after photon A has already landed, the interference pattern is recovered. Seriously, let me repeat that because it's wild. By obscuring the markings produced earlier, we get the wave pattern back on photon A's screen. It makes it seem as though our delayed choice literally reached backward in time and changed how photon A behaved when it hit the slits. It feels exactly like we are rewriting history. But are we really?
Before we start calling up Doc Brown and concluding that we're sending information backward in time, we have to snap back to reality. As physicist Johannes Fankhauser points out, this setup is actually a standard Bell-type scenario. And the resolution to this whole paradox is, in his own words, surprisingly trivial. There is absolutely no backwards-in-time influence present here. It's an illusion of retrocausality, basically masked by the strange way we interpret quantum states.
Theoretical physicist Sean Carroll perfectly summarizes the reality of what's going on here. He explicitly states there's no need to invoke retrocausality to explain the delayed choice experiment. He points out that the particle hasn't truly irreversibly interacted with the messy, complex environment of the universe yet. Instead, it has merely become entangled with a single recording spin, our twin photon. Because the system remains relatively isolated, we're simply allowed to contemplate measuring it in a few different ways.
If that still sounds a bit abstract, think of the whole thing like an encrypted diary. When photon A hits the screen, it leaves a completely scrambled, overlapping pattern. On its own, if you just look at it, it looks like a completely random mess of particle hits. There is no visible interference pattern whatsoever. You literally cannot read the hidden wave message embedded in that static until you receive a highly specific decryption key. And that key? That's the data collected from measuring photon B.
Which brings us to the actual mechanical truth of the whole experiment. The total pattern of signal photons on the primary screen never shows interference on its own. To see that beautiful wave pattern, the experimenter actually has to take the data from photon A and mathematically correlate it with the data from photon B. This requires sorting the superimposed, messy data into 4 distinct streams using a process called coincidence detection. You are essentially just filtering the messy screen based on what happened to the twin photons. So you aren't changing the past at all. You are just sorting the present data in a highly specific way.
And here is the absolute nail in the coffin for time travel. Coincidence detection requires a classical signal to compare those entangled twins. If you want to know if 2 detectors lit up within a nanosecond of each other, you physically have to run a wire or send a traditional signal between them. That means this entire comparison process can operate no faster than the speed of light. Because extracting this which-way information requires a normal, slower-than-light channel, absolutely no information is being communicated backward in time.
So, what should you really take away from all this? Ultimately, this explainer shows us that the universe isn't just letting us rewrite history based on our whims. Instead, it illustrates the profoundly delicate role that decoherence and entanglement play in measuring our present reality. The math doesn't require retrocausality. It requires us to fundamentally rethink what a measurement truly is when quantum systems are deeply intertwined. And I think it leaves us with a pretty provocative final question. In a universe woven together by quantum entanglement, can we ever truly separate the observer from the observed? Or are we just decoding reality one entangled coin at a time? Thanks for joining me on this deep dive. And as always, keep questioning the nature of your reality.